let us solve the problem together. So, as you see here, we have an unbounded interval of integration. And because the denominator does not vanish, and that is a rational expression, this means that this is an improper integral of type 1. We do not have any discontinuity on this interval for my integrand, but the interval is of course unbounded. So in order to solve the problem, we have to use the definition of these type of improper integrals. So the question mark is actually equal to the integral of from 2 to r. R is a positive number greater than 2 of the same integrand and then we take the limit and send r to infinity. So what we are supposed to do, we are supposed to calculate this definite integral, which becomes a function of r, and then from that function of r, we take the limit and send r to infinity. If this limit exists and it becomes a number, that number is equal to the question mark that we are looking for. Okay, and in order to find this integral, because this function is continuous everywhere, so we can use Newton's theorem by finding an antiderivative of this function. Okay, so we first concentrate on finding an antiderivative of that function. So I calculate the integral 2x plus 1 over x squared plus 1 dx. But hopefully you know that for these type of integrals that I have a rational function as my integrand, in which the degree of the denominator here 4 is greater than the degree of the denominator 1, we have to use the method of partial fractions. So what we do, we decompose this fraction 2x plus 1 over x squared plus 1 as the sum of 3 partial fractions, a over x, and then b over x squared, and then finally cx plus d over x squared plus 1. Then I need to find a, b, c, and d. Okay, what we can do, I can multiply everything on both sides by x squared plus 1. If I multiply this on the left, this is cancelled, this is left. And if I multiply this here, x is cancelled, the leftover is multiplied by a. If I multiply that expression here, x squared is gone. What is left is supposed to be multiplied by b, and the same thing for the third fraction. So let me just do that. If we do that, the left side becomes 2x plus 1. The right side becomes a, x squared plus 1. The middle one becomes b times x squared plus 1. And the last one becomes cx plus d multiplied by x squared. So I expand the right hand side. It becomes ax cubed plus ax plus bx squared plus b. And then I have cx cubed plus dx squared. And now what I do, I take this one, with that one I factor x cubed out. I take these together, I factor x squared out, and ax and b are alone. So what I do, I would write a plus cx cubed, and then I will have b plus dx squared. Then I have ax plus b. And now look, the right hand side is a third degree polynomial. The left hand side is a first degree polynomial. We want to make them identical. This cannot happen unless the coefficients are correspondingly equal. So the coefficient of x cubed on the right is a plus c. The coefficient of x cubed on the left is 0 because there are no cubic term there. So this means that a plus c should be 0. For the same reason, b plus d should also be equal to 0. but a should be equal to 2 and b should be equal to 1. So this is a system of 4 equations in principle and 4 unknowns, but 2 of the unknowns have already been found. So what I do, from the first equation, and that a is 2, c becomes minus 2, and from the second equation, b is 1, so d becomes minus 1. Now everything now is in order, so instead of a, b, c, and d, I put these numbers that I found, and when I want to integrate this, I break my integral into 3 integrals. Okay, so if, let me call this integral I, so I becomes equal to, a is 2 here, 2 goes out, I have integral dx over x. The next one is b over x squared, but b is 1, so this becomes simply dx over x squared. And the third one, I have minus 2 minus 1, I pull a minus sign out, so this becomes integral of 2x plus 1 over x squared plus 1. And then I have dx here. All of these integrals, as you will see, are very simple to calculate. The first one is just 2 ln of absolute value of x plus, the other one is minus 1 over x. And for the third one, I decompose it into 2 more integrals. So I take this part and that part separately. I have a minus sign here. So this becomes minus integral of 2x over x squared plus 1 dx, and then minus integral of 1 over x squared plus 1 dx. Okay, for the last one, we have a simple formula, so it's a very famous formula. So we have integral of 1 over x squared plus a squared dx is just 1 over a arctangent of x over a, of course plus a constant. Here we should also have a positive. So for the last integral, I can immediately use that. So you see that 1 can be interpreted as 1 squared, and it means that a is 1 in this problem. So essentially this is just arctangent of x. And for the next one, if you don't mind, let me call it I, and let me calculate I. Then I will actually combine all the rules. So here, this is I, so that's not a good place to write, it is not visible, so let me write here, this is I, and then I calculate I like this. For calculating I introduce a new variable t, say t is equal to x squared plus 1, I differentiate both sides, dt becomes 2x dx, so the integral I becomes integral of, instead of 2x dx, I put dt, and instead of x squared plus 1, I put t. So what I get is dt over t, which is simply ln of absolute value of t. I replace t with x squared plus 1. Because x squared plus 1 is always positive, I don't need the absolute value signs, so I remove them with a pair of brackets. So this becomes just simply ln of x squared plus 1. Okay, so now if I finally want to write the final answer for I becomes equal to 2 ln of absolute value of x minus 1 over x. I is minus ln of x squared plus 1, and then minus arctangent of x, and of course plus a constant c, but because we are supposed to calculate the definite integral from 2 to r, we don't need to write c. C, whatever c is, it is cancelled. Now because we are supposed to calculate the limit in the future, near future, so let me just try to rewrite this a little bit differently. So you know that this expression can be written as ln. This power of 2 can be raised here, so absolute value of x to power 2 is just x squared. Okay, and then I can combine this one with the last one, and write it as one single ln. So I can write it as ln of x squared divided by x squared plus 1. Okay, and then I have minus 1 over x, and then I have minus arctangent of x. So this is I. Okay, so now let me call this integral j of r, because that will be a function of r. So what is j of r? J of r is actually I, which is calculated between 2 and r. So I replace every appearance of x with r. So this gives me ln of r squared over r squared plus 1, and then minus 1 over r minus arctangent of r, and then minus, I put 2 instead of x, so this becomes 4 over 5, but remember I have a minus sign, so this becomes minus ln of 4 over 5 plus 1 over 2 plus arctangent of 2. Yes? Now I need to question mark is equal to the limit of j of r when r goes to infinity. So what happens? If r goes to infinity, the limit of this part is simply 1, but ln of 1 is 0. So this vanishes. 1 over r goes to infinity, that also vanishes. But arctangent of r, when r goes to infinity, the limit is pi over 2, but I have a minus sign here. So the limit becomes minus pi over 2. The rest of it has nothing to do with r, so I have to copy and paste all of them. So finally, my answer to this question is actually I have 1/2. Then let me write the positive 1 arctangent of 2, and then I have minus ln of 4 over 5, and then minus pi over 2. So that is also the answer to this integral. I hope that this video was useful for you. Until the next video, be safe and goodbye. Thank you.